Hello everyone. Hope you had a nice day. Welcome to Lesson 5, Properties of Solids. This is still related to our previous topics such as the intermolecular forces of attraction and to the properties of matter. So we already finished properties of liquids. Now we're going to tackle properties of solids. Specifically, we're going to compare the properties of crystalline and amorphous solids to classify the different types of crystal according to the binding forces and to relate the external properties of different types of solid to the components. So let's define first what is a solid. As we all know, solid has a definite shape and volume. It is very rigid and compact. That is why it cannot flow. The particles cannot flow and therefore it can't be called a fluid. Fluid are substances that can flow such as liquids and gases. However, in case of solid, it cannot flow but only vibrate. So what causes this definite shape and volume? It is depending on the structure of the material or the unit cell. So let's define first the category or nature of solids. We have two, the crystalline and the amorphous solid. Let's define first crystalline solid. Crystalline solids are solid material whose components such as atoms, ions, or molecules are arranged in an orderly manner. So it has a well-defined arrangement. It has a flat surface and sharp edges. Example of which are salt, sugar, and some gems. So how are molecules being arranged in microscopic level? The crystal basic unit is called unit cell. This is the smallest portion which shows the complete pattern of the particles or the arrangement of the atoms within the crystal. We have isometric, hexagonal, tetragonal, trigonal, and the likes. Aside from that, we have the packing arrangement types, which can be categorized as a simple cubic, body-centered, and then face-centered. If these unit cells come together, it forms a crystal lattice. So this crystalline lattice makes the shape of the overall external structure of crystalline solid. And how can we know the atomic structure or the unit cell or unit packing type of these crystalline solids? We have the instrument called X-ray diffraction, wherein a stream of X-ray directed at the crystal diffracts and scatters as it encounters atom, and the resulting scattered rays produce a pattern, which can you see here in case of graphite crystal. In this film, you can see the formation of the atoms inside. We have four types of crystalline solids according to the bonding interactions. So this is the keyword here. Bonding interactions. We have metallic solids, ionic solids, covalent network solids, and molecular solids. First, we have metallic solids. Of course, from the name itself, you can identify that these solids are brought together by different types of metal atoms. So it has held together by metallic bonding, and it has a variable hardness, melting point, and it is also conducting. Ionic solids are composed of ionic compounds. So it is held together by the attractive forces between ions, oppositely charged ions to be exact. It has a high melting point, it is brittle, and it is hard and non-conducting. Unless these ionic solids are molten, so if it's already in liquid state or you put it in a solution, it can be used as a conducting material. Next, we have covalent network solids. So it is composed of network of atoms held together by covalent bonds. It has a high melting point, hard, and non-conducting. So the keyword in covalent network solid, it is a network of repetitive atoms, such as allotropes of carbon. For molecular solids, these are types of solids uh, brought about by the bonding forces of H bond, particularly this type, H bonding, and other intermolecular forces such as dipole-dipole moment, London dispersion forces, and the likes. It has a low melting point and it is non-conductive. So let's take a look at the examples of each type. We have the crystalline solids. Here is the sodium crystal, and then aluminum crystal, and we have here copper crystal. So these are the elements and components are obviously metals. Ionic crystalline solids. Example is halide. This is commonly known as rock salt. Again, it is held together by ionic forces or ionic bonding. It is composed of positive and negatively charged ions. Next is the covalent network solids. Such as quartz with a chemical formula, silicon dioxide, SiO2, and then diamond. This is an allotrope of carbon. And then graphite on the other side. Still the same as the diamond, it is composed of carbon atoms. I will call it carbon allotropes. Last one is the molecular crystalline solid, example of which is dry ice and sugar. Okay, so if you notice, dry ice, which is H2O, and then sugar are composed of C12, H22, and then oxygen 11 atoms. These two are covalent, held together by covalent bonding. However, it is also held together by H bonding forces. So this is the strongest forces in a compound. Therefore, it is classified into molecular crystalline solids. So just a reminder, do not be confused between covalent network and molecular crystalline solids. The clue here is the hydrogen. So if the material is a compound and it's composed of too much hydrogen, then it is a molecule or a molecular crystalline solid. If it is a covalent bond and it's very repetitive like carbon atoms, it is a covalent network solid. So this is the structure representations of molecules of these solids in terms of pictures. This is metallic solid. We have here the arrangement of positive and negative charges in ionic solids. Again, the components are ions. In case of metallic solids, the components are metals. And then for covalent networks, it is repetitive atoms or arrangements of one or more covalent bond, such as silicon and carbon. For molecular solids, when you see hydrogen there and the strongest force that interacts in the compound is H bonding, that it is classified as molecular solid. So can you see the difference? It is basically not a network. That's why it has that kind of structure. In the ionic solid, it is very rigid, and you can see the arrangement of positive and negative charges. And then for metallic solids, these are arranged in a certain manner, such as either cubic phase, simple phase, and center. In terms of atoms, so that you can see the electron cloud, this is ionic bonding. As you can see, it's alternating pattern. Negative, positive, negative, then positive. And then for covalent bonding, they just share electrons. This is C4, as you can see there. And then we have here metallic bonding, where there are free electron, mobile. When you say mobile, it has a movement. So it is a mobile sea of electrons that are the main reason why metallic metals or metallic solids are conductive. Next is the molecular forces held together by H bonding. Okay. So those are the 4 types of crystal. Now we're going to define the next category of solids, which is amorphous solids. We have here A, which means without, and then morph, which means form. So therefore, amorphous solids is defined as a solid without a definite order or whose components are arranged in disorderly manner. Example of which are charcoal, rubber bands, glass papers, weights, and plastic lunch boxes. So you can see the shape. It doesn't have a certain shape, and it's very, sometimes it is elastic and flexible. So these are the properties of amorphous solids compared to crystalline solids, which are very hard, and you can use it as for cutting materials, for tools, because it has a sharp edge and very rigid and compact sides. This is the structure of amorphous solid. It has this very unorganized pattern. It has many spaces between them, and it doesn't have a definite unit cell or packing type of unit cell. Okay, so it can be noted that as temperature of crystalline solid is increased, the particles vibrate back and forth about its lattice point. The crystal becomes less ordered. So what does that mean? So when you subject any kinds of solids to a hot or cold temperature, depending on the degree, the formation or the particles within the structure will become disoriented and will change, of course. So it will either becomes soft, will become brittle, or it will disintegrate. Sometimes, at a certain point, it will melt, will become a liquid, such as dry ice. If you boil it, of course, it will return to its liquid state. Okay, let's do a practice problem. Let's classify these examples to the type of crystal. Let's take a look at sodium first. Okay, so first and foremost, find these compounds or atoms in the periodic table so that you will know the classification of these crystals. Okay, so let's start with sodium. Sodium is a metal. Therefore, when the sodium atoms form a crystalline lattice, it will become a metallic crystal. So I will put it here, sodium. Next, we have sodium chloride. Sodium chloride is what type of compound? So take a look at the components. We have sodium ion and chlorine an ion. So these are made up of ions, two oppositely charged ions. It is an ionic compound, therefore, in solid state, it is an ionic crystal. Next, we have calcium oxide. Calcium oxide. So let's take a look at this compound. What are the components? We have calcium ion, and then oxide ion. Again, these are two oppositely charged particles. Calcium oxide is an ionic compound, therefore I will classify it as an ionic crystal. Next, sugar with the chemical formula C12H22 and oxygen 11. These have hydrogen bond, and these are also covalently bonded molecule. However, it doesn't have a repetitive, it doesn't have a network. Therefore, it can be classified as a molecular crystal. Next, quartz. Quartz with a chemical formula silicon dioxide. As you can see, these atoms are both nonmetals, and it doesn't have a hydrogen on the bonding on the compound. Therefore, it is a covalent network. Next one is diamond. So, diamonds are composed of several carbon atoms. It is a network of carbon atoms in a crystalline lattice. Therefore, it is classified as a covalent network crystal. Next is water molecule. Water molecule. It's a molecule. It is composed of hydrogen and oxygen. It has a hydrogen bonding. Therefore, it is a molecular crystal if water becomes ice. Crystal. Okay, and last one, we have zinc. Zinc is a metal. It is in the transition metal part of the periodic table. Therefore, it can be formed as metallic crystal. Okay, so hope you understand the topic. The clue is just take a look at the components of the compound so you can identify or determine whether it is metallic, ionic, covalent, and molecular crystal. Okay, so that's all. Thank you.